I'm Jinzhao from China Academy of Railway Sciences Corporation Limited. My topic is on real contact force identification model and its application. There are 4 parts in this presentation. First is the introduction on the background of the node identification. Then is real and real contact force identification model. The third part is on safety evaluation by use of the predicted contact force, and the following is the conclusion. It's well known real contact force is an important indicator to evaluate railway safety. Therefore, it's very important to monitor the real contact force and to evaluate the safety of track vehicle system by using the monitor data accumulated during high-speed railway operation, such as we use the node reduction index, derailment coefficient to evaluate the safety of the vehicle and the system dynamic. Generally speaking, there are 2 methods to obtain the contact force between the track and the vehicle systems. One way is to measure the contact force by measuring the wheel sets. Another one is to obtain the contact force by indirect method. That is a node identification model. From this model, if we consider the force as the input and the acceleration is the output, we always use this model in simulation. On this presentation, we solve the inverse model. That's we consider the acceleration as the input and the force is the output. In this presentation, we will present a homographic model for identification of real contact force by combined with the optimal control theory, real clip theory, and Kalman filter method. In this model, additional for the contact force, we also can obtain the contact parameters, such as the lift of the wheel sets. This is the model. First, we to do the node identification. First, we need to transfer the dynamic governing equation into the state space equation. And this governing dynamic equation is well known. It's also named as MCK model. And the M is the general mass, and C is the diameter matrix, and K is the stiffness matrix. And this model also called the multi-body contact model. And in this model, we use the calculus theory to solve the group force between the wheel and the rail. Here, first, we transfer the dynamic model into the state space equation of the vehicle system by use of numerical method. And in the numerical method, the acceleration and the velocity is discretized by some formula. And after the transformation, we obtain this state equation is named as xi plus 1 equal to axi and plus bfi. And here the xi is the state variable, and the fi is the force. This is the formula of the matrix of A and B, and this is used in the state space equation. Generally, we identify the vertical contact force and the total lateral force of the wheel set by minimize the measured acceleration and the simulation acceleration. The simulation acceleration is from the state equation. And it also means to solve a program problem. The object function is defined as 1/2 and EX n transpose P n E n, and also the inverse prediction and the detailed detection you can find in the paper. And these are some formula. First, we solve the vertical contact force. In the vertical contact force is easier to obtain by use of the vertical acceleration. And to obtain the lateral force, is maybe you use the vertical acceleration and the lateral acceleration. And the vertical contact force and the total force applied on the wheel set can be corrected positively using Kalman method. This means first we do the positive correction, because during the identification, the contact force may be fluctuate. Maybe that there is some noise in this predicted contact force, which will affect the result. Here we introduce the Kalman method to filter the contact force during the identification processes. Here, maybe you in the review in some paper you can find the identification of the vertical force and the lateral force. The lateral force also is the total lateral force of the wheel set. But how to get the lateral force of every X box, every wheel is very difficult. From this Kalman equation, we can see that there are four variables. There are four variables. One is two is the vertical force, contact force, and another two is the lateral force. But there is only three Kalman equations. So this is a yield-posed problem. You cannot identification the contact force directly, because it's a yield-posed problem. Here we introduce the loading contact solver to transform this problem into a stable problem. That means we introduce the lateral displacement to connect the left and right lateral force. Then we transfer these two variables of the two lateral force into one variable. That means the lateral displacements. Then we solve three variables by use of three equations. That's a stable problem. These are some model validation by use of simulated data and field test data. The simulation data is obtained by some multi-board dynamics software such as Adams-Rail and SimPack. You can see this. The red one is the identified force, and the blue one is the inspection force and obtained from the prediction model. For vertical contact force, it agrees well. But for the natural force, there is some difference. And furthermore, for the field, test field, or the difference is a little large. The test field is obtained from the high-speed comprehensive inspection train shown in the right bottom, which run in channel, and with the speed of 300 kilometers. The simulation and we use the correlation coefficient to verify the model, and the correlation coefficient of the vertical force and the predicted force is more than 0.8. Furthermore, in this prediction model or this identification model, we can obtain the contact force. Furthermore, we also can obtain the contact parameters, such as the lift of the wheel sets, which can be used to evaluate the safety of the tracking and vehicle system status. Usually, there are three methods to evaluate the safety of the system. One, we use some index calculated from the contact force, such as the derailment coefficient. Another one uses the lift of the wheel set. Currently, we use the composite index. That's we combine the lift index and the contact force index. The reason is you can see that in some cases that the derailment coefficient is very large, but it does not derail because the natural displacement of the wheel set is small, and the wheel set will come back, so it does not derail. You can see at this figure. So we compare these two indexes. We introduce the wheel set lift and compare with the contact force index. We divided the safety dome region into three parts. One part is safer. Another part is possible derailment, and the third part will derail. And in this evaluation method, we need to obtain the lift of the wheel set. It's very difficult to obtain, and in this model, we obtain the lift of the wheel set by this prediction model. Here, the conclusion is that in this presentation, we present a homographic wheel contact force identification model by use vehicle acceleration, also by use of the track geometry irregularity. It can solve the yield-post problem of deficiency of equation and the lack of inspection data. In this identification model, we obtain the contact force and the wheel set lift in the same time. Thank you very much.